On April 17, 2026, engineers at NASA's Jet Propulsion Laboratory sent a command into deep space, and roughly 23 hours later, one of the last working instruments aboard Voyager 1 went dark. The instrument was called the Low Energy Charged Particle Experiment. It had been running since 1977. For nearly 5 decades, it tracked the flow of charged particles streaming out from the Sun and measured how that flow changed as Voyager pushed deeper into space. When Voyager crossed into interstellar space in 2012, the LSEP was one of the tools that helped scientists understand exactly what that crossing meant. It was, in other words, not a minor piece of equipment. It was a core part of why the mission existed, and they turned it off because they had no choice. Here's the thing most people don't realize about Voyager 1 right now. The spacecraft isn't in danger of crashing or breaking down in some dramatic way. There's no malfunction, no emergency. The problem is simpler and harder than that. It's running out of power. Not all at once, slowly, steadily, about 4 watts per year, the way a candle burns down rather than blows out. And the engineers at JPL have spent the last several years making a series of increasingly painful decisions about which parts of the spacecraft they can afford to keep alive and which ones they have to let go. The LEC was the latest sacrifice. It won't be the last. To put the power situation in concrete terms, Voyager 1 launched generating around 470 watts of electricity. That's roughly what a standard kitchen appliance draws. Not a lot, but enough to run the spacecraft's instruments, its computers, its heaters, its radio. Now, after nearly 50 years, that number has dropped dramatically. The spacecraft is operating on a fraction of what it started with, and every system still running is drawing from the same shrinking pool. When engineers ran the numbers in early 2026, they realized that a continued drop in available power could trigger an automatic fault protection response, the spacecraft shutting itself down in ways that might not be recoverable. So they acted first. They chose what to sacrifice before the spacecraft chose for them. That's the situation Voyager 1 is in right now. A machine launched in September 1977, now more than 15 billion miles from Earth, still functioning, still transmitting, still doing science, but just barely. And the people keeping it alive are working with a budget measured in watts, making triage decisions that would have been unimaginable when the mission began. Because when the mission began, nobody expected any of this. Voyager 1 was designed for a 4-year mission. 4 years. The plan was straightforward. Fly past Jupiter. Fly past Saturn. Gather data. Done. The spacecraft would then drift off into space. Its job complete. No longer anyone's responsibility. Nobody at JPL in 1977 was planning for 2026. Nobody was thinking about instrument shutdowns 5 decades later, or about managing a power budget on a spacecraft operating in interstellar space. They were thinking about getting the thing off the ground and through 2 planetary flybys without anything going catastrophically wrong. What actually happened is one of the stranger stories in the history of science. The 4-year mission became a 50-year mission. The spacecraft meant to study 2 planets ended up crossing the boundary of the solar system entirely. The probe that was supposed to go quiet in the early 1980s is still, right now, sending back data from a region of space no other human-made object has ever reached. And the scientists who've spent their careers on this mission are now doing something that nobody planned for and nobody has a real template for: managing the slow, careful, deliberate end of the most successful spacecraft ever launched. Each shutdown matters. The Lexi-B going dark isn't just a line in a status report. That instrument had been measuring particle flows across the entire outer solar system, through the termination shock, through the heliosheath, into true interstellar space. The data it gathered helped rewrite our understanding of where the sun's influence ends and the galaxy begins. Turning it off means that measurement stops. That window closes. You don't get to reopen it. At the same time, shutting it down bought the remaining systems more time. The two instruments still running, one measuring plasma waves, one measuring magnetic fields, get to keep running a little longer. The radio stays on. The signal keeps coming. The conversation between Earth and this improbable machine continues, at least for now. That's the calculation the JPL team is living inside. Every decision is a trade. Every watt saved somewhere is a watt that goes somewhere else. Every instrument lost is a capability gone forever, but also a reason the spacecraft survives another few months, another year, maybe longer. It's an impossible position to be in, and they've been in it in various forms for years. What makes it stranger is that none of them signed up for this. They signed up to work on a spacecraft. What they ended up doing is something closer to keeping a piece of history alive with their bare hands, one difficult decision at a time, across a distance so vast that their commands take nearly a full day to arrive. Voyager 1 was never supposed to be here. It was never supposed to reach interstellar space, never supposed to last 5 decades, never supposed to become the thing it became. And now the people responsible for it are watching it approach its end, instrument by instrument, watt by watt, with the specific grief of people who know exactly what they're losing and why it can't be saved. But to understand what Voyager is about to lose, you have to understand what it was never supposed to become. In the mid-1970s, mission planners at NASA noticed something that wouldn't happen again for another 176 years. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were arranging themselves in a configuration that made a single spacecraft flyby of all 4 genuinely possible. Gravity assists from one planet could slingshot a probe toward the next, cutting travel time dramatically. Without that alignment, a mission to Neptune alone would have taken decades using the technology of the time. With it, you could theoretically visit 4 worlds in roughly 12 years. The window opened in 1977. It would not open again until 2153. NASA moved fast. The mission that would become Voyager was originally conceived as something fairly modest. 2 spacecraft, a quick tour of Jupiter and Saturn, 4 years of flight time, and then done. That was the plan. Send them up, collect data on the 2 largest planets in the solar system, and call it a success. Nobody was promising anything beyond Saturn. The budget didn't allow for it, and frankly, getting to Saturn at all was ambitious enough. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed 2 weeks later on September 5th. Despite launching second, Voyager 1 was on a faster trajectory and would reach Jupiter ahead of its twin. Both spacecraft carried 10 scientific instruments each, designed to measure magnetic fields, charged particles, plasma, infrared radiation, and more. They were built to last 4 years. That was the expectation going in. Here's where things get interesting. Jupiter came first. Voyager 1 reached it in March 1979, and what the cameras sent back was something no one had fully anticipated. Scientists knew Jupiter was a gas giant, a swirling monster of a planet. What they did not know was what its moons looked like up close. Io was the revelation. This moon, roughly the size of our own, turned out to be the most volcanically active body in the entire solar system. Voyager 1 caught active eruptions in real time, plumes of material firing hundreds of kilometers into space. Before that image came back, nobody had ever seen an active volcano anywhere beyond Earth. Io rewrote the rulebook in a single photograph. Europa offered something quieter but equally striking. Its surface was smooth, cracked with long reddish lines that looked almost like a shattered eggshell. The implication was hard to ignore. Liquid water, possibly an ocean, underneath that frozen shell. Ganymede and Callisto added their own textures to the story. Jupiter's moons weren't dead rocks, they were worlds. Saturn was next, and it did not disappoint. Voyager 1 arrived in November 1980. The rings, which had been observed through telescopes for centuries, turned out to be far more complex than anyone had modeled. There weren't just a few broad bands. There were thousands of individual ringlets, some braided, some with strange gaps caused by the gravitational pull of small embedded moons. The structure of those rings was one of the more beautiful and baffling things the mission returned. Scientists are still working out the details today. Titan, Saturn's largest moon, was another target. Voyager 1 made a close pass and found a thick orange atmosphere, denser than Earth's at the surface. The cameras couldn't see through it. That decision to prioritize Titan meant Voyager 1's trajectory after Saturn sent it on a path up and out of the plane of the solar system. It would not be visiting Uranus or Neptune. That job would fall to Voyager 2. And this is where the 4-year mission started refusing to stay dead. Voyager 2 had also completed the Jupiter and Saturn flybys. It reached Jupiter in July 1979 and Saturn in August 1981. At that point, the primary mission was technically finished. Both spacecraft had done what they were built to do. The question was whether to attempt what mission planners quietly called the Grand Tour, sending Voyager 2 onto Uranus and Neptune, two planets that had never been visited by any spacecraft at all. The trajectory made it possible. The spacecraft was still functioning. The window was still open. NASA extended the mission. It was not a small decision. Uranus was 12 years away from launch. Neptune was 12 years after that. They would be committing to a mission that wouldn't finish until 1989. Voyager 2 reached Uranus in January 1986. The planet was strange in ways nobody had predicted. Its axis is tilted so severely, about 98 degrees, that it essentially rolls around the sun on its side. Its moons were unlike anything in the inner solar system. Miranda, a small moon, had terrain so varied and dramatic that geologists weren't sure how to explain it. Cliffs that drop for miles, canyon systems, ancient cratered plains sitting right next to young grooved terrain. It looked like something had broken it apart and put it back together imperfectly. Then Neptune, in August 1989, more than 12 years after launch, Voyager 2 arrived to find a deep blue planet with the fastest sustained winds ever recorded in the solar system, up to 1,200 miles per hour, And then there was Triton, Neptune's largest moon, orbiting in the wrong direction. Most moons orbit in the same direction their planet rotates. Triton does the opposite. That retrograde orbit strongly suggests it was captured, pulled in from somewhere else, probably the Kuiper Belt, and it's slowly spiraling inward. In a few 100 million years, Neptune's gravity will tear it apart. Voyager 2 found geysers on Triton's surface, erupting dark material through a thin nitrogen atmosphere. Geysers. On a moon at the edge of the solar system, in temperatures close to absolute zero. By the time Neptune was in the rear view, the two Voyager spacecraft had collectively visited 4 planets, dozens of moons, and returned data that reshaped planetary science in ways that are still being processed. The missions that were supposed to last 4 years had run for 12. What started as a brief tour had become the longest planetary expedition in history. The planetary tour was over. The primary mission was complete, and Voyager 1 was still very much alive. Once the Saturn flyby was done, Voyager 1 had one direction left to go. Out, just out. There was no next planet on the itinerary, no scheduled encounter waiting on the calendar. The planetary tour was finished, and Voyager 1 was pointed toward a part of space that no spacecraft had ever reached. Engineers kept the transmitters on. The spacecraft kept sending data, and quietly, without much fanfare, it just kept going. To understand what that journey actually means, you need to understand something about the structure of our solar system that most people don't think about. The sun doesn't just sit there radiating light. It's constantly releasing a stream of charged particles called the solar wind. And that wind pushes outward in every direction at roughly 1 million miles per hour. Over billions of years, that relentless outflow has carved out a vast bubble in the surrounding space. That bubble is called the heliosphere. Everything inside it, every planet, every moon, every asteroid, every spacecraft we've ever launched, is inside the sun's sphere of influence. The boundary where the solar wind finally runs out of energy and gets pushed back by the material between the stars is called the heliopause. And beyond that line is interstellar space. Here's how big that bubble is. Pluto, which most people think of as sitting at the outer edge of the solar system, is nowhere near the heliopause. Pluto orbits at roughly 40 astronomical units from the Sun. The heliopause sits somewhere around 120 astronomical units out. Voyager 1 had to travel 3 times further than Pluto just to reach the edge of our solar system. That's not a small gap. That's billions of miles of additional journey after the last planet disappears from view. Voyager 1 crossed the orbit of Pluto in 1990. Think about what that means. This spacecraft, launched in 1977, had already traveled further than any planet in our solar system, and it still had decades of travel ahead before it reached the actual boundary. It was moving at about 38,000 miles per hour. At that speed, you could circle the Earth in less than an hour. And it still took all those years just to get to that point. That's the scale you're dealing with out here. Through the 1990s and 2000s, scientists tracked Voyager 1 carefully. They were watching the data from its instruments, looking for signs of change. The spacecraft was still detecting the solar wind. It was still clearly inside the heliosphere. But the numbers were shifting. The solar wind was slowing down, becoming less energetic. There was a boundary called the termination shock, where the solar wind drops abruptly in speed as it starts running into the interstellar medium. Voyager 1 crossed that in 2004. That was a significant milestone. It meant the spacecraft was in the outer layer of the heliosphere, a turbulent zone scientists call the heliosheath. But it still wasn't out. What followed was years of debate. The instruments were sending back data that was genuinely hard to interpret. The heliosheath turned out to be stranger and more complicated than anyone expected. Scientists argued about where exactly the heliopause would be, what the crossing would look like in the data, and whether Voyager might slip through it without a clean, obvious signal. There was no line painted in space. There was no moment where a light would blink on and say, "You have left the solar system." The determination would have to come from the data, and the data required interpretation. Then, in 2012, the numbers shifted in a way that became impossible to argue with. The charged particles inside the heliosphere, the ones being generated by the sun, dropped off dramatically in the data, almost overnight by spacecraft standards. At the same time, cosmic ray readings spiked. Cosmic rays are high-energy particles from sources outside our solar system, and the solar wind had been acting as a kind of shield, deflecting many of them before they could reach the inner heliosphere. When Voyager cleared the heliopause, that shield was gone. The cosmic ray count jumped by roughly 9% in just a few days. The solar wind particles essentially disappeared. That was the crossing. August 25, 2012. Scientists announced it officially in 2013, after careful analysis of the data, and the number they landed on was 121 astronomical units from the Sun. That translates to roughly 11.2 billion miles. At that distance, the sunlight reaching Voyager was so faint it would have been invisible to the naked eye. The spacecraft had left the sun's domain entirely and entered the space between the stars. Now here's what interstellar space actually is, because most people imagine it as emptiness. It's not. The region between stars is filled with gas and dust. Thin, cold, sparse compared to anything near a planet, but not nothing. Astronomers call it the interstellar medium, and it has its own density, its own magnetic field, its own structure. It's the material that was left over from ancient stellar explosions, the raw stuff from which new stars and planets eventually form. Voyager 1 is moving through that material right now, and the instruments still running on the spacecraft are measuring it. The plasma density, the magnetic field orientation, the particle environment. We've modeled the interstellar medium from Earth for decades, using telescopes and theoretical physics. Now we have something actually in it, sending back direct measurements, and some of what it's found doesn't match the models. The heliopause sits at a different location than many predictions suggested. The magnetic field in the local interstellar medium is oriented differently than expected. The interstellar medium is stranger and more structured than the simpler picture we'd built from a distance. By March 2026, Voyager 1 was 172 astronomical units out. That's roughly 16 billion miles from Earth. A radio signal traveling at the speed of light takes more than 23 hours to make that trip one way. The spacecraft is so far away that the Sun from Voyager's position would look like nothing more than an unusually bright star in the sky. Brighter than other stars, yes, but just a point of light. You wouldn't be able to see Earth at all. And yet the spacecraft is still pointing its antenna back toward that tiny bright speck, still generating power from its slowly decaying plutonium, still sending data at 160 bits per second across a gulf that most people have no framework to visualize. It's not lost. It's not drifting silently. It is actively measuring the environment around it and transmitting those measurements home. Engineers on the ground receive the signals, decode them, and publish the results. Papers are being written right now based on data from a spacecraft launched almost 50 years ago by people who are mostly retired or gone. For the first time in human history, we had a probe in interstellar space and it was still talking to us. Voyager 1 doesn't run on solar panels. By the time the spacecraft crossed the orbit of Saturn, it was already too far from the sun for solar power to be useful. The sunlight out there is roughly 100 times weaker than what you'd get in Earth orbit. You couldn't build a solar panel large enough to run a wristwatch on that. So the engineers had to find another way. What they came up with is called a radioisotope thermoelectric generator, and the basic idea is elegant in its simplicity. You take a radioactive material, in this case plutonium-238, and you let it decay. Radioactive decay produces heat. You run that heat through a device called a thermocouple, which converts the temperature difference directly into electrical current. No moving parts, no combustion, just physics, running quietly in the dark for decades. Each Voyager spacecraft launched with 3 of these generators, and together they produced about 470 watts of electricity at the start of the mission. That's roughly what you'd use to run a couple of desktop computers. Plutonium-238 was a particularly good choice for this. Its half-life is about 87 years, which means it decays slowly enough to be useful over a very long mission. It doesn't burn out fast. It just gradually, steadily produces less and less heat as the fuel depletes. That was always the plan. The designers knew from the beginning that the power supply would fade. What they didn't plan for was a spacecraft still operating nearly 50 years later, still needing that power, still asking for more than the generators can give. Here's where the math gets painful. Voyager loses roughly 4 watts of power every year. 4 watts doesn't sound like much, but over 47 years that adds up to something close to 190 watts gone. The spacecraft that launched with 470 watts is now operating on something in the neighborhood of 280 watts, and that number keeps dropping. Every year the budget gets a little tighter. Every year the engineers have a little less to work with. And it's not just the plutonium running out. The thermocouples themselves degrade over time. These are the devices converting heat into electricity, and they don't last forever. Even if the plutonium were somehow replenished, the conversion efficiency would still drop. So the power loss is coming from 2 directions at once. Less heat being produced, and less of that heat being turned into usable electricity. The result is a spacecraft that's being slowly starved of the one thing it needs to stay alive. To understand what this means in practice, think about what a spacecraft actually needs power for. It needs power to run its science instruments. It needs power to operate the radio transmitter that sends data back to Earth. It needs power to keep the onboard computers running, the ones that control orientation and execute commands from the ground, and it needs power to run heaters. That last one is the one most people don't think about. Out in interstellar space, the temperature is close to absolute zero. Certain components on the spacecraft, fuel lines, electronics, mechanical systems, have to be kept above a minimum temperature or they stop working permanently. So heaters run constantly, pulling power just to keep the hardware from freezing solid. Turn off a heater, and you risk killing whatever it was protecting. The question engineers face is which systems you're willing to risk, and which ones you absolutely cannot lose. This is the triage that's been happening for years now. It's a slow, methodical dismantling. Engineers look at the power budget, identify what's drawing current, and then ask themselves, if we turn this off, what do we lose, and can we live without it? Sometimes the answer is easy, a backup system with a primary still running. Shut it down. An instrument that was designed for the planetary phase of the mission, doing nothing useful in interstellar space. Shut it down. But the easy decisions ran out a long time ago. What's left now are the hard ones. Heaters protecting components that might still be needed. Instruments that are still returning genuinely useful scientific data from a region of space no other probe has ever reached. Every choice carries a cost. Shut down a heater, and you might save enough power to keep an instrument running for another year. But if the temperature in that compartment drops too far, you might lose something else entirely, something you didn't even intend to sacrifice. In February of this year, Voyager 1 experienced an unexpected power drop during a routine roll maneuver. Engineers realized they were dangerously close to triggering what's called the undervoltage fault protection system. That system is designed to protect the spacecraft by automatically shutting down components when power gets too low. The problem is that an automatic shutdown isn't a controlled shutdown. If the system activates unexpectedly, you could lose something critical, something you didn't choose to lose in a sequence you didn't plan for. And recovering from that, from 15 billion miles away, is not guaranteed. So the engineers acted first. They turned off the low-energy charged particle instrument in April, taking control of the decision before the spacecraft made it for them. That's what the triage looks like at this stage. You're not just managing power, you're managing risk. You're trying to stay one step ahead of a failure cascade that, if it starts, you may not be able to stop. What makes this particularly difficult is that you can't just pop the hood and look inside. Every diagnosis happens through data that takes nearly 24 hours to arrive. Every intervention is a command sent into the void, with no confirmation for almost a day. If something goes wrong in response to an action taken on the ground, the team won't know about it until the following morning. And by then, the situation may have changed again. You're operating on delay, always on delay, managing a machine you cannot see, cannot touch, and cannot immediately reach. The people doing this work have been doing it for decades in some cases. They know this spacecraft, they know how it behaves, how it responds, where it tends to run warm, what its quirks are, and they've spent years developing a kind of fluency with a machine that is, by any reasonable measure, ancient. The hardware predates personal computers. The software has been rewritten multiple times from the ground. The flight team has essentially kept a 1970s spacecraft alive by sheer persistence and ingenuity, adjusting to every new constraint the power budget throws at them. But persistence can only take you so far when the fuel is running out by physics. Plutonium-238 doesn't care how dedicated the engineers are. The thermocouples don't improve because the team works harder. The laws of thermodynamics don't make exceptions. The power will keep declining at roughly 4 watts per year, And eventually there won't be enough to run the transmitter, and that will be the end of the conversation. What the team is doing now is buying time. Carefully, deliberately, painfully buying time. One shutdown at a time, 1 watt at a time. Every heater they turn off, every instrument they sacrifice, every system they decide they can live without, goes into that calculation. Every watt they save is a little more time, and time is the one thing they cannot manufacture. To send a message to Voyager 1 right now, you press send and then you wait. Not for seconds, not for minutes. You wait for 23 hours and change before that signal even arrives at the spacecraft. Then you wait another 23 hours for any response to make the trip back. So if you sent a command on Monday morning, you wouldn't know if it worked until Wednesday. That's not a metaphor for bureaucratic slowness. That's the actual physics of operating a machine that is now roughly 16 billion miles from Earth and getting farther every second. Here's where things get uncomfortable. That number, 16 billion miles, is almost impossible to hold in your head in any useful way. Let's try to make it concrete. Light travels at 186,000 miles per second. It takes about 8 minutes for sunlight to reach Earth from the sun. At that same speed, a signal takes over 23 hours to reach Voyager 1. That means Voyager 1 is more than 23 times farther from Earth than the Sun is. And by late 2026, the gap will have widened to a full light day. 24 hours of signal travel, one way. Voyager 1 will become the first human-made object in history to cross that threshold. 1 light day from home. The Sun, by comparison, is about 8 light minutes away. The scale difference there is not subtle. Think about what 1 light day actually means for the people running this mission. An engineer at JPL notices something odd in the telemetry. She drafts a command, checks it, gets it approved, and sends it out through the deep space network. Then she goes home. She sleeps. She comes back the next morning, works a full day, goes home again. She sleeps a second night. She comes back Wednesday morning, and she finds out if the spacecraft did what she asked. That is the operational rhythm of talking to Voyager 1. Every decision carries a 2-day lag. Every course correction, every instrument adjustment, every diagnostic query, all of it happens in slow motion across an ocean of empty space. And the signal itself, when it finally comes back, is almost nothing. 160 bits per second. That's the data rate Voyager 1 transmits at. For comparison, a typical home internet connection runs at tens of millions of bits per second. The connection you use to stream a video is roughly 100,000 times faster than what Voyager 1 can send home. A single photograph on your phone would take hours to transmit at that rate. What Voyager is sending back isn't images anymore. It's instrument readings, numbers, the raw output of 2 science detectors measuring the environment around them. Even that trickle of data requires extraordinary effort to receive. Here's what it actually takes to pick up Voyager's signal. The spacecraft transmits with about 22 watts of power, roughly the output of a refrigerator light bulb. By the time that signal crosses 16 billion miles and arrives at Earth, it is so faint that it's almost indistinguishable from background noise. To detect it at all, NASA uses the Deep Space Network, a system of enormous dish antennas located in California, Spain, and Australia. The main dishes are 70 meters across. That's wider than a 20-story building is tall. And sometimes even a single dish isn't enough. Engineers have to combine the output of multiple antennas simultaneously, essentially stitching their signals together to pull Voyager's whisper out of the static. This is what receiving a message from interstellar space looks like. It's not a crisp radio broadcast. It's a 22-watt signal that has spent a full day crossing the void, arriving at 160 bits per second into an antenna the size of a small stadium. The transmission window isn't always available either. The Deep Space Network serves other missions too. Time on the big antennas gets scheduled and allocated. The Voyager team doesn't have unlimited access. They work within those windows, sending and receiving what they can, knowing that each session is one of a finite number of conversations still remaining. When a session is allocated, the planning begins weeks in advance. The Voyager team must prepare meticulously, knowing they might not secure another window for quite some time. Engineers pre-script their commands, anticipate possible responses, and think through contingencies before the window opens. There's no room for improvisation across a signal delay of that magnitude. What happens 16 billion miles away must be decided on Earth first, committed to the command sequence, and then observed after a 2-day wait with no ability to adjust mid-course. The cost of a mistake, in time, in power, in remaining mission lifespan, makes every interaction a carefully calculated step. That's the part that sits differently when you think about it. The engineers at JPL know something the spacecraft doesn't. They know the power budget, they know the decline rate, they know roughly how many years of communications remain. Every exchange they have with Voyager 1 is one exchange fewer on the total count. They're writing letters to something 16 billion miles away and waiting 2 days for a reply, and they can see the stack of blank pages getting thinner. There's a specific kind of patience required here that most technical fields don't demand. A software engineer can run a test and see results in milliseconds. A mechanical engineer can watch a part under stress in real time. The Voyager team makes a decision, then waits nearly 2 days to see if it was the right one. And if it wasn't, if the spacecraft did something unexpected, or the command had an unintended effect, they start the 2-day cycle over again to correct it. The margin for error shrinks as the power shrinks. A command that causes an unexpected power draw could trigger the spacecraft's fault protection system, which could cascade into shutdowns they'd have to spend days trying to reverse. Caution isn't optional. It's baked into the physics. By November 2026, when Voyager 1 crosses that 1 light day milestone, a signal sent from Earth at 8 a.m. on a Monday won't arrive until 8 a.m. Tuesday. The reply won't land until Wednesday morning. 3 days for a single exchange. There is no other operational spacecraft anywhere near that distance. Nothing we've built has ever had to communicate across a gap this wide. Voyager 1 didn't set this record by going fast. It set it by going for nearly 50 years without stopping. That's the reality of operating a spacecraft at the edge of the solar system. Every conversation is a 2-day commitment, and you only have so many left. The engineers at JPL have one more card to play. After years of shutting things down, turning off heaters, sacrificing instruments one by one, just to keep the spacecraft breathing, the team has come up with something different. Not another shutdown, a reconfiguration, a sweeping, all-at-once overhaul of how each spacecraft manages its remaining power. They're calling it the Big Bang, and the name is not accidental. This isn't a small adjustment. It's the biggest intervention in the mission's history, and it has to work the first time. Here's what the Big Bang actually involves. Each Voyager spacecraft still has powered devices running in the background, systems that draw electricity even when they're not actively contributing to science. The plan is to swap those out. Turn off the power-hungry components. Turn on lower-draw alternatives that can do the same jobs for less energy. The goal is to find enough headroom in the power budget to keep the science instruments running, and potentially even bring back instruments that were already shut down. It sounds straightforward. It isn't. The reason it isn't straightforward comes down to something called the undervoltage fault protection system. Every Voyager spacecraft has one. It's an automatic safeguard, built in at launch, designed to protect the probe if power drops too low. If the available voltage falls below a certain threshold, the system kicks in on its own and starts shutting down components to prevent a catastrophic failure. That sounds like a good thing. The problem is that an automatic shutdown triggered by the fault protection system is not controlled. It's not planned. The system makes its own decisions about what to cut, and some of those decisions could be unrecoverable. Engineers might lose components they can't get back in a sequence they didn't choose from 16 billion miles away. That's what they're trying to avoid. The Big Bang is essentially a controlled version of what the fault protection system would do on its own if things got bad enough. Do it deliberately, do it carefully, and you keep control of the outcome. Let the spacecraft do it automatically under duress, and you might lose everything. So the stakes are not small. If the maneuver goes wrong, if the power balance tips in the wrong direction during the swap, you could trigger exactly the automatic response you were trying to prevent. And recovering from an undervoltage fault on a spacecraft that's been in space for nearly 50 years, operating on margins that are already razor thin, is not a process with a guaranteed happy ending. Every recovery attempt carries its own risks. Every command sent in response takes 23 hours to arrive, and another 23 hours to confirm. By the time you know something went wrong, it's already been going wrong for nearly 2 days. Here's where things get uncomfortable. The team can't test this on Voyager 1 first. Voyager 1 is the priority. It's the one farther out, the one already deeper into interstellar space, the one with less margin for error. So they're using Voyager 2 as the test case. Voyager 2 has slightly more power remaining. It's a bit closer to Earth, and it's in a similar enough configuration that a successful result there gives engineers real confidence before they attempt the same thing on its twin. Voyager 2 goes first. The plan puts its Big Bang in May and June of 2026. The team monitors every step. They watch the telemetry, track the power levels, confirm that the lower draw alternatives are holding up, and make sure the science instruments are still functioning on the other side of the swap. If all of that checks out, they take what they've learned and apply it to Voyager 1 in July. That gap between Voyager 2 and Voyager 1 matters. It's not just scheduling. It's the difference between a blind leap and a calculated one. Every piece of data from Voyager 2's reconfiguration is a data point that makes Voyager 1 safer. Not safe. Safer. There's no version of this that's without risk. What makes the Big Bang genuinely hopeful, not just desperate, is what it could give back. Remember the low-energy charged particle experiment? The instrument shut down on April 17th. That shutdown wasn't permanent by design. It was a triage decision. the best available option to keep power levels stable after an unexpected drop. But if the Big Bang works, if it frees up enough power that the spacecraft has headroom it doesn't currently have, the LECP could come back. An instrument that went dark in April 2026 could potentially be reactivated. That's not guaranteed, but it's possible, and the team knows it. That possibility matters more than it might sound. The low-energy charged particle experiment has been collecting data about the particles streaming through interstellar space since Voyager 1 crossed the heliopause in 2012. That data is irreplaceable. There is no other instrument anywhere near this region of space. Losing the LECP meant losing one of the only direct measurements of what the environment beyond our solar system is actually made of. Getting it back, even briefly, would be scientifically significant in a way that's hard to overstate. The three remaining science instruments on Voyager 2, the plasma wave subsystem, the magnetometer, and the cosmic ray subsystem, are also part of what the Big Bang is designed to protect. The goal is to keep all three running on Voyager 2, and to keep the plasma wave subsystem and magnetometer alive on Voyager 1 for as long as possible afterward. Together, the two spacecraft would function as something like a pair of weather stations in interstellar space, one ahead of the other, both measuring the environment that no mission before them ever reached. But none of that happens if the Big Bang fails. What you have here is a team of engineers who have already spent years making the hard calls, turning things off, letting things go, saying goodbye to instruments that have been running since the Ford administration. And now they've decided that instead of just managing the decline, they're going to try to reverse some of it. One carefully planned, all-at-once reconfiguration, tested first on the spacecraft they can afford to risk more, then applied to the one they can't afford to lose. It's a high-wire act performed across 16 billion miles, with no safety net and no second chances. After nearly 50 years and the loss of one instrument after another, Voyager 1 is down to 2. Not 10, not 5, 2. The plasma wave subsystem and the magnetometer. That's what's left of a spacecraft that launched with 10 science instruments in 1977. And those two are still working, still collecting data, still doing something that no other machine on Earth or in space can do. Here's what those instruments actually are. The plasma wave subsystem listens. That's the simplest way to put it. It detects oscillations in the plasma around the spacecraft, electric and magnetic waves moving through the charged particles that fill interstellar space. If you converted those oscillations into sound, you'd hear something like a low, eerie hum. Scientists have done exactly that, and the recordings are genuinely strange. The magnetometer does what the name suggests. It measures magnetic fields. Out in interstellar space, those fields come not from the sun, but from the galaxy itself. The large-scale magnetic structure of the Milky Way, shaped over billions of years by ancient supernovae and stellar winds that have nothing to do with our own star. Together, these two instruments are essentially building a portrait of the environment Voyager is traveling through. And that environment is not what anyone expected. Before Voyager crossed the heliopause in 2012, scientists had models for what interstellar space should look like. They had predictions about plasma density, about how the sun's magnetic influence fades and the galactic field takes over, about the thickness and structure of the boundary region itself. Those models were reasonable. They were based on decades of careful physics, and they were wrong in ways that are still being worked out. The heliopause, the boundary where the sun's outward-flowing solar wind finally gives way to interstellar space, turned out to be sharper and more defined than most models predicted. The density of plasma on the far side was higher than expected. The orientation of the interstellar magnetic field didn't match the predictions either. It's tilted differently than the models assumed, which has real implications for how our solar system moves through the galaxy and how the heliosphere is shaped by the pressure pushing in from outside. None of this would be known without Voyager 1. That's not an exaggeration, it's just true. You can model interstellar space from Earth. You can make inferences from observations of other stars and stellar systems. But direct measurement, actually being there, actually sampling the plasma, actually reading the magnetic field, that requires a probe. And the only probe we have ever put in interstellar space is this one. Think about what that means in practical terms. Every day that the plasma wave subsystem and the magnetometer keep running, scientists are getting data from a region of space that is completely inaccessible by any other means. There's no telescope that can measure local plasma density 16 billion miles from Earth. There's no ground-based instrument that can tell you what the interstellar magnetic field feels like at that location. The only way to know is to send something there and have it report back. Voyager 1 is the only thing we've ever sent, and it's still reporting. What the team at JPL wants, what they're working toward with every power decision, every instrument shutdown, every watt they carefully preserve, is to keep those two instruments running as long as possible. The goal is to turn Voyager 1 into something like a weather station in interstellar space. Not a flashy mission with cameras and atmospheric probes, just a persistent sensor sitting in the dark, measuring what's around it and sending the numbers home. Stripped down, quiet, doing one job. That's not a consolation prize. The data coming back from those two instruments right now is some of the most scientifically valuable information being collected anywhere in the space program. Voyager detected a significant increase in plasma density when it crossed into interstellar space, about 40 times denser than what it was measuring inside the heliosphere. That single measurement reshaped models of the heliosheath and the structure of the boundary region. Scientists are still publishing papers on what it means, and there's something bittersweet about it. This spacecraft launched with cameras that photographed volcanic eruptions on Io, with instruments that mapped the composition of Saturn's rings, with enough capability to conduct a full scientific survey of 4 planetary systems. Now it's down to 2 sensors measuring things you can't even see. No images, no drama, just a magnetic field reading and a plasma wave signal, transmitted home at 160 bits per second across 16 billion miles of nothing. But here's the thing. Those 2 measurements, quiet and unglamorous as they are more scientifically irreplaceable than almost anything else flying right now. Because this is the only spacecraft in interstellar space. Everything it measures first. Everything it detects is a discovery, by definition, because we have never had eyes here before. The New Horizons spacecraft, which flew past Pluto in 2015, is heading in the same general direction. But it won't reach the heliopause for decades. There's no other mission in the pipeline that will get there sooner. Voyager 1 isn't just the first, it's also currently the last and the only. So when engineers at JPL calculate power budgets and decide which systems to keep alive and which to sacrifice, those two instruments sit at the top of the list, not because of sentiment, because of what they're doing. Because nowhere else in the human scientific enterprise is there an instrument collecting data that simply cannot be collected any other way. Two instruments, 16 billion miles away, measuring a place no other spacecraft has ever been, and still sending the data home. Bolted to the side of each Voyager spacecraft is a 12-inch gold-plated copper disc. It is the most ambitious piece of mail ever sent. It's a phonograph record, the kind you'd play on a turntable. NASA engineers sealed it inside a protective aluminum jacket, along with a cartridge, a needle, a set of instructions etched in symbolic language explaining what it is and how to use it. The whole thing is designed to survive in space, essentially forever. Gold doesn't corrode. Copper doesn't rust. Out in the cold of interstellar space, with no atmosphere to degrade it and no weather to wear it down, that disk could last 1 billion years without significant damage. Whatever finds it will find it largely intact. That was the point. Carl Sagan chaired the committee that decided what went on the record. He described it as a message in a cosmic bottle. Humanity tossing something into an ocean so vast that the odds of anyone finding it are almost unmeasurably small. He knew that. The whole team knew that. And they did it anyway, because the act of sending it said something about us regardless of whether anyone ever picked it up. Sagan put it plainly. The very fact that we launched this bottle into the cosmic ocean says something hopeful about life on this planet. Not optimistic, necessarily. Hopeful. Here's where the project gets genuinely interesting. The committee had a nearly impossible job. They had to compress the entirety of human civilization, our science, our music, our languages, our faces, our world, into something that could fit on a single record and be understood by a receiver who had never encountered a human being, heard a human voice, or seen our planet. No shared language, no shared cultural references, no assumptions about biology or perception. They had to communicate across the largest possible gap imaginable, to an audience they couldn't define, using a format the audience might not recognize, and they had roughly a year to figure out how. What they landed on was 115 images encoded in analog form, covering everything from the structure of DNA to a nursing mother to the inside of a supermarket. Then came the sounds of Earth: thunder, rain, wind, surf. A croaking frog, the cry of a newborn, footsteps, laughter, a kiss. Then greetings spoken aloud in 55 different languages, representing more than 4 billion people at the time of the launch. Then 90 minutes of music. That music list is worth sitting with for a moment. Bach appears 3 times. So does Beethoven. There's a Navajo night chant, a Peruvian wedding song, a Azerbaijani folk melody, gamelan from Java, a Pygmy girl's initiation song from Zaire. Louis Armstrong plays, Blind Willie Johnson plays, and then there's Chuck Berry. Johnny B. Good made the cut. Not everyone was pleased about this. One critic on the committee, the musicologist Alan Lomax, pushed back hard, arguing that rock and roll was adolescent music and didn't belong on a record representing humanity to the cosmos. Carl Sagan's response was simple. There are a lot of adolescents on the planet. That exchange captures something essential about what the golden record actually was. It wasn't meant to be a greatest hits collection curated by a committee of experts presenting only the most refined and elevated version of humanity. It was meant to be real, messy, plural, contradictory, alive. Chuck Berry belongs on that record for the same reason the sounds of a crying infant do. Because that's us. You don't get to edit out the adolescent parts just because you're embarrassed by them. The cover of the record is its own remarkable piece of work. Any civilization that recovers the spacecraft and gets this far would need to know what they're holding. So engineers designed a set of illustrations in universal symbolic language. No words, no alphabet. Just diagrams based on physics and mathematics that any technologically advanced civilization would presumably understand. There's a drawing of the record itself, with the stylus in the correct starting position. Binary notation shows the correct rotation speed. 1 full revolution every 3.6 seconds. A side view diagram shows the playing time for a single side, roughly an hour, encoded in binary. Another diagram uses the hydrogen atom, the most common element in the universe, as a basic unit of measurement. Any reader, a physical reference to anchor everything else. A pulsar map shows the position of our solar system relative to 14 known pulsars, so that whoever finds this knows where it came from. And there's a diagram of our solar system itself, with a small arrow indicating which planet launched it. Think about what that required. The cover is written in a language that doesn't exist yet, a language invented specifically for this moment, designed to be readable by minds that might be completely unlike ours. The team had to think from first principles about what knowledge any intelligent spacefaring civilization would necessarily share with us. Mathematics, physics, the behavior of hydrogen, pulsar timing. These are the shared reference points. They built the entire instruction manual out of those building blocks alone. The greeting section is its own rabbit hole. The original plan was to record the United Nations delegates speaking in their native languages. That ran into logistical problems almost immediately. So the committee ended up recording new greetings at Cornell University, using people from various language departments. The speakers were given no script. The only instruction was that it had to be brief, and it had to be a greeting to possible extraterrestrials. What people said in that situation, without preparation, speaks to something genuine. Most of them fell back on warmth. Hello, we send you good wishes. We hope to meet you someday. The simplest possible message, in 55 different voices, is still essentially the same message. Kurt Waldheim, the UN Secretary General at the time, opened the record with a formal statement on behalf of the people of Earth. President Jimmy Carter contributed a written message, printed as part of the image set, describing a civilization of 240 million Americans among 4 billion humans on a small planet orbiting an ordinary star. Carter wrote that we were attempting to survive our time so that we might live into theirs. That line carries more weight now than it probably did in 1977. The 115 images cover an enormous range. Mathematical definitions, physical and chemical units, the solar system, Earth from space, anatomy, human reproduction, a nursing mother, children, a supermarket, rush hour traffic, a sunset, a man eating a grape. The images were encoded as audio signals on the record itself, requiring the finder to reconstruct them, a layer of puzzle solving built directly into the format. Here's the thing about all of it taken together. The committee argued about every single choice. They debated which pieces of music were worthy, that images were too strange, which greetings were too long, which sounds were too obscure. They had finite space and infinite options. Every inclusion was also an exclusion. Every choice to include Bach's Brandenburg Concerto No. 2 was also a choice not to include something else. There's no way to know if they got it right, because there's no standard to measure it against. They were inventing the standard as they went. Whatever they chose, it was ours, the best argument humanity could make, in under 2 hours, for why we were worth finding. Of everything on the golden record, one item is harder to wrap your mind around than all the rest. Not the music, not the 55 languages, not even the 115 images encoded in analog form on a copper disc bolted to the side of a spacecraft that is now 16 billion miles from Earth. Those things are extraordinary, but you can at least picture them. You can understand what it means to record a greeting or press a piece of music into a disc. What Ann Druyan contributed is something different, something that takes a moment to actually land. Here's what happened. In the summer of 1977, Druyan was serving as the creative director of the Golden Record Project. She and Carl Sagan had just fallen in love. And we mean just. They had declared their feelings for each other only days before she walked into Bellevue Hospital in New York City and sat down in a lab, where technicians wired her up to a computer designed to read her brain activity and her heartbeat. The machine would convert those signals into sound, and that sound would go on the record. She had 1 hour. She had planned out a kind of mental itinerary, a structured sequence of thoughts she wanted to move through during the recording. She thought about the history of Earth, about the slow accumulation of life across billions of years, about the civilizations humans had built and the problems those civilizations still hadn't solved. She thought about what it would feel like to be a person, alive on a small planet, aware for the first time in that planet's history that you could send something beyond it. And she thought about being in love, about Carl Sagan, about what that felt like in the specific and unrepeatable way it felt in those particular days when everything was new. All of that, the full hour of it, was captured as electrical signal. Then it was compressed. The hour-long recording was packed down into roughly a minute, and that compressed data was encoded directly onto the golden record, not as a description of her thoughts, not as a summary. The actual electrical output of her brain, the literal pattern of her mind at work, is on that disc. Think about what that means for a second. When we talk about everything else on the record, we're talking about representations. A photograph represents what something looks like. A musical recording represents what something sounds like. A spoken greeting represents what someone wanted to say. But Druyan's contribution isn't a representation of anything. It's the thing itself. The electrical record of a human nervous system, mid-thought, mid-feeling, compressed and encoded and sent into space. You can't get closer to a person than that. A photograph of someone's face is a layer removed. This is the activity of the mind behind the face. There's something else worth sitting with here. Druyan didn't know, going into that hospital room, that she and Sagan would end up together. The relationship was so new that the future of it wasn't yet clear. What she knew was that she was in love right then, in that specific moment, and that the machine she was wired to was going to record whatever her brain did with that feeling. She had no way to perform it or curate it. Whatever happened in her nervous system, that's what got recorded. And now it's out there. Voyager 1 is currently moving away from Earth at roughly 38,000 miles per hour. It crossed into interstellar space in 2012, and it has been pushing deeper into that environment ever since. At this distance, a radio signal takes more than 23 hours to reach it. But the golden record isn't sending signals. It doesn't need to. It's just riding, silent and intact, in its gold-plated aluminum jacket, attached to the side of a spacecraft that is never coming back. Ann Druyan's brainwaves are on that record. Her heartbeat is on that record. The thoughts she had about Earth's history, about civilization, about what it felt like to be a human being who had just fallen in love, all of that is encoded in the grooves, and it will be there in 100 years, in 1,000, in 1,000,000. There is no mechanism in interstellar space to degrade it on any timescale that matters to us. The record will almost certainly outlast every person alive today. It will outlast every building currently standing on Earth. It will very likely outlast the civilization that made it. Here's where things get genuinely hard to hold in your head. The compressed electrical record of a human mind in love is traveling through interstellar space right now, at this moment, as you're listening to this. Not a metaphor for that. Not an artistic representation of that idea, the actual thing, the actual data. Moving further from Earth every second, in a direction it will never reverse. Druyan has talked about this over the years, about what it means to know that something so intimate is so far away. She described the experience of that recording session as one of the most moving of her life, not because of what it produced, but because of what she was trying to do. She was trying to send the experience of being human to something that had never encountered a human being. And the most honest version of that she could offer was exactly what the machine recorded, a mind doing what minds do, feeling what they feel, thinking through everything that seems to matter. That's what's riding on Voyager 1. Not a statement about humanity, not a carefully worded summary. An hour of a person's interior life, compressed to a minute, encoded on gold-plated copper, attached to a machine built by human hands in the 1970s, that is now so far from Earth, it takes a full day for light to make the trip. Voyager is not just a scientific instrument. It is, in a very real sense, a piece of a person. And that piece is still out there, still moving, still going further every hour of every day. Somewhere beyond the edge of the solar system, the thoughts of a woman in love are riding a gold-plated disk through interstellar space, and they will be out there long after everything she ever knew is gone. When the last signal fades, Voyager 1 doesn't stop. That's the part that's hard to absorb. Sometime between 2030 and 2036, the power will drop below the threshold needed to run the radio. The transmitter will go quiet. The Deep Space Network antennas will stop picking up anything from that direction. And from that moment forward, we will have no idea what's happening out there. But the spacecraft will still be moving. At roughly 38,000 miles per hour, it will keep going exactly the way it's been going for decades, in a straight line, outward, into the dark. There's nothing to slow it down. No friction, no drag, No gravity strong enough at that distance to pull it back. It just goes. Here's the thing most people don't think about when they hear that Voyager is running out of power. They imagine the mission ending. But the mission ending and the spacecraft ending are two completely different things. The mission ends when we lose contact. The spacecraft doesn't end at all. It continues for timescales that are almost impossible to hold in your head. Let's start with where it's going. Voyager 1 is heading in the direction of the constellation Ophiuchus. That's not a destination. There's no planet there it's aimed at. No waypoint someone plotted. It's just the direction the physics of the planetary Flybys sent it decades ago, and it has been moving that way ever since. In roughly 40,000 years, it will make a close pass of a star called Gliese 445. Not a collision, it will pass at a distance of about 1.6 light years. But in the scale of interstellar space, that's close. That's a near miss by cosmic standards. 40,000 years. Take a second with that number. 40,000 years ago, modern humans were living in Europe and painting on cave walls. The caves at Lascaux, the ones with the bulls and the horses, those paintings are about 17,000 years old, less than half the time between now and when Voyager reaches Gliese 445. The oldest known cave art is around 40,000 years old. We were making pigment from ochre and blowing it through hollow bones onto rock. That's where we were as a species when Voyager 1 was, in a sense, just being born into the future. By the time it makes that pass, whatever humans are, if humans still exist at all, will be as unrecognizable to us as we would be to the people in those caves. And after the flyby of Gliese 445, Voyager keeps going. That's not the end. That's just a milestone along a journey with no scheduled terminus. It will continue outward through the Milky Way for as long as the galaxy itself holds together. There's no mechanism in place to stop it. Nothing waits out there to catch it. It will drift past star systems and through the spaces between them for longer than human civilization has existed by a factor of thousands. Now consider what that means for Earth. The Sun is about 4.6 billion years old. It has roughly another 5 billion years left before it begins to expand into a red giant. When that happens, it will swell outward, engulfing Mercury, Venus, and almost certainly Earth. The inner solar system ends, but Voyager 1 will not be in the inner solar system. It will not be in the solar system at all. It will be somewhere in the galaxy, long past any reach of what the Sun does to its own planets. The spacecraft built by human hands in the 1970s will almost certainly outlast the planet that produced it. That's not a metaphor. That's just the math. There's something strange about sitting with that fact. Everything we know, every city, every language, every piece of music ever recorded, every person who ever lived, is tied to this planet. And this planet has an expiration date. A long one, yes, but fixed. Voyager doesn't share that constraint. The void it's moving through imposes nothing on it. No erosion, no weather, no radiation intense enough at those distances to degrade the craft in any meaningful way on these timescales. The golden record bolted to its side, the one carrying the sounds of Earth and the brainwaves of Ann Druyan, and greetings in 55 languages, that record will still be there, intact, waiting. Think about what you'd need to destroy Voyager 1 now. You'd need a direct physical collision with another object, an asteroid, a rogue planet, something with mass. The odds of that in the emptiness between stars are extraordinarily small. Space is not crowded. Between star systems, you can travel for light years without encountering anything large enough to matter. Voyager is almost certainly safe from collision for timescales that dwarf the current age of the universe. It will still be out there when the universe is older than it is now. The engineers who built it are gone, or nearly gone. The generation that watched the launches in 1977 is aging out. The people making decisions about Voyager today weren't born when it left Earth, and yet the craft they're tending keeps moving, indifferent to all of it, racking up distance at 38,000 miles per hour every single hour of every single day, growing farther from everything that made it. When the radio finally goes quiet, there won't be a dramatic moment. There won't be a last transmission with a clear goodbye encoded in it. The signal will just degrade past the point of recovery, and then it will be gone. The antennas will listen for a while longer, the way you might keep checking your phone after you know someone isn't going to call back. And then that will be over too. But the spacecraft won't know any of that. It will still be moving. In 40,000 years, it will pass close to another star, carrying a gold disk and the brainwaves of a woman who has been dead for tens of thousands of years, and it will keep going after that. There are people at the Jet Propulsion Laboratory who have spent more of their professional lives on Voyager 1 than on anything else they've ever done. That's not a poetic exaggeration. Some of the engineers currently managing the mission were working on it in the 1970s. Others joined in the 1980s or 1990s and never left. For them, Voyager 1 isn't a historical artifact or a symbol. It's a machine they know intimately. Its quirks, its failure modes, the way it responds to commands, the particular signature of its transmissions. They've spent decades reading its telemetry the way a doctor reads a patient's chart, looking for anything that shouldn't be there. Here's the thing most people don't appreciate about what that actually means. When you work on a spacecraft for 30 or 40 years, you don't just know it technically, you know it the way you know a place you've lived in for a long time. You know where the problems are. You know what sounds right and what doesn't. You've been through enough crises with it that the relationship becomes something harder to define than professional. And the crises have been real. In 2022, Voyager 1 started sending back corrupted data from its attitude articulation and control system. Garbled telemetry that didn't match any recognizable pattern. The team spent 5 months diagnosing the problem from 15 billion miles away, eventually tracing it to a single faulty chip in an onboard computer. They couldn't replace the chip. They couldn't physically touch anything. What they could do was reroute the software, redistributing the affected code across other parts of the computer's memory to work around the damage. And they did it. A spacecraft launched in 1977, running on hardware that predates the personal computer, was reprogrammed in deep space by engineers, sending instructions that took 23 hours to arrive. That's the level of intimacy we're talking about. So when the decision came in April 2026 to shut down the low-energy charged particle experiment, it wasn't a bureaucratic call. It wasn't an easy line item cut from a budget. That instrument had been running continuously since 1977. It had operated for longer than most of the engineers currently on the team have been alive. Turning it off meant acknowledging, in a very concrete way, that the spacecraft is running out of time. Not someday. Now. Think about what that room must feel like. You've got a team of people who've dedicated careers to keeping this machine alive. They understand better than anyone what it costs to lose each instrument, not just scientifically, but in terms of what it says about where things stand. Every shutdown is a data point. Every instrument that goes dark is one fewer reason the spacecraft has to keep drawing power, which sounds like efficiency, but in practice it just means the end is getting closer in a way that's impossible to ignore. The grief involved in that process is real, even if it's quiet. It's not the dramatic kind. Nobody is going to cry in a press conference. These are professionals, and they treat the work professionally. But quiet grief is still grief. When you've spent your career keeping something alive, and you're now the person making the call to start turning pieces of it off, that lands somewhere. It has to. What makes it stranger is that the spacecraft isn't alive. Everyone in that room knows that. It's aluminum and circuits and decaying plutonium, transmitting data at 160 bits per second across an incomprehensible distance. It doesn't know they're there. It doesn't know its instruments are being shut down. It just responds to commands, or it doesn't. Sends data back, or it doesn't. Keeps moving in a straight line regardless of what anyone on Earth decides. But that's not how it feels from inside the mission. It can't be. You don't spend 40 years diagnosing problems on something without developing a relationship with it that goes beyond the clinical. These engineers know this spacecraft better than any human being has ever known any machine in the history of exploration. They know its limits. They know what it can and can't handle. They've argued over its systems in meetings and lost sleep over its anomalies and celebrated its recoveries. That's not nothing. That shapes how you experience the end of something. There's also the weight of knowing what they're responsible for. Voyager 1 is the most distant human-made object that has ever existed. It crossed into interstellar space over a decade ago. It's measuring an environment that nothing else has ever measured. Every decision these engineers make, which instrument to prioritize, which heater to sacrifice, which system gets power, and which one doesn't, affects the only data stream coming from interstellar space. That's not a small thing to carry into a meeting. Every watt is a real choice with real scientific consequences, and the people making those choices are doing it under the constant awareness that there are no replacements, no second chances, no other spacecraft close enough to take over. The Big Bang Power Reconfiguration isn't just an engineering maneuver. From inside that mission, it's probably something closer to a last push. A chance to extend the timeline a little, to keep more instruments running a little longer, to delay the silence that everyone can see coming. If it works, the team gets more time, more data, maybe even the chance to bring one of the recently shuttered instruments back online. And if it doesn't work, if the undervoltage protection triggers and components start shutting down in ways that can't be recovered, then that's the end, and everyone in the room will have been there when it happened. That's what the people at JPL are living with right now. Not just the technical challenge of keeping a 50-year-old spacecraft functional across 16 billion miles of space, but the knowledge of what's coming, instrument by instrument, watt by watt, conversation by conversation. They know this machine better than anyone. They know how it sounds when it's working and how it sounds when it's struggling. They've kept it alive longer than anyone thought possible, and now they're using every tool they have to keep it going just a little further. They're the last people who will ever talk to it, and they know it. There is no backup. That's the part that doesn't get said enough when people talk about Voyager 1's decline. It's not just that we're losing a spacecraft. It's that we're losing the only spacecraft that can do what this one does. There is no redundancy here. There is no second probe positioned nearby, ready to pick up where Voyager leaves off. What Voyager 1 is doing right now, in real time, is something nothing else in existence can replicate. Here's what you need to understand about where Voyager 1 actually is. It's in interstellar space, not approaching it, not near the boundary, through it, past it, on the other side. It crossed the heliopause in 2012, and that crossing was itself a years-long argument among scientists about whether it had actually happened. The data was strange. The expected signatures weren't quite where models said they'd be. The magnetic field was oriented differently than anyone predicted. The plasma density jumped in ways that surprised the people who had spent decades building the models that were supposed to anticipate exactly this. The interstellar medium turned out to be weirder than the textbooks said. That's the thing about going somewhere no one has ever gone. You find out your maps were wrong. The heliopause, the boundary where the sun's influence gives way to the broader galaxy, behaves differently than our best models suggested. Before Voyager crossed it, we had theoretical frameworks built from indirect measurements, from observations made inside the bubble our sun creates. We thought we had a reasonable picture. We didn't. The actual boundary region was more turbulent, more complex, and structured differently than the models said it would be. Some of those models had to be rebuilt from scratch after Voyager's data came in. And here's the thing most people don't realize. That data is still coming in. Right now, the plasma wave subsystem and the magnetometer aboard Voyager 1 are measuring conditions in interstellar space that we have no other way to access. Not approximately, not through inference, directly. Voyager is sitting out there in the actual environment between stars, taking readings and sending them home at 160 bits per second across 16 billion miles. That signal, that trickle of information, barely faster than a fax machine, is the only direct line we have into a region of the galaxy that no other human-made object has entered. Let's talk about what comes closest. New Horizons launched in 2006. It flew past Pluto in 2015, and it's been heading outward ever since. By some measures, it's the 5th fastest spacecraft ever launched, and it won't reach the heliopause for somewhere between 20 and 30 years. Maybe more. It isn't close. It isn't a near-term alternative. In terms of reaching the interstellar medium, New Horizons is decades behind where Voyager 1 was in the 1990s. The two spacecraft aren't in the same conversation right now when it comes to interstellar science. Voyager 2 is also out there, and it crossed the heliopause in 2018, about 6 years after its twin. It's measuring interstellar space from a different direction, heading toward the constellation Pavo rather than Ophiuchus, which actually makes it scientifically complementary to Voyager 1. 2 data points in 2 directions. That's the entire data set. The complete picture of what interstellar space looks and feels like, from a direct measurement standpoint, fits inside 2 aging spacecraft launched in 1977, with computers less powerful than a modern wristwatch. When you lay it out like that, the stakes of every instrument shutdown become clearer. Each instrument that goes dark isn't just a piece of hardware being retired. It's a measurement capability that disappears from the only platform that can make that measurement. You can't compensate for it with a ground-based telescope. You can't model your way around it. The interstellar medium has to be measured from inside the interstellar medium, and the only things we've ever put inside it are Voyager 1 and Voyager 2. Some of what Voyager has already sent back has forced real revisions in how astrophysicists think about the structure of the heliosphere itself. The boundary region is not a clean line. There's a zone of transition, turbulent and magnetically complex, that sits between the termination shock and true interstellar space. Voyager spent years crossing that region, and what it recorded there changed the working models of how our solar system interacts with the galaxy around it. The interstellar magnetic field, the large-scale field that permeates the space between stars, is tilted differently relative to the heliosphere than the predictions said it would be. That's not a minor discrepancy. That's a structural revision to our understanding of the local galactic environment. And the measurements are still coming. Every day the plasma wave subsystem is running. It's logging wave activity in a medium we otherwise have no access to. Every day the magnetometer is operating. It's recording field strength and orientation at distances no instrument has previously reached. This data is not being duplicated anywhere. It's not being supplemented. When Voyager 1 makes a measurement, that measurement either gets recorded and transmitted home, or it doesn't happen. That's the weight of what the JPL team is managing. Every decision to shut down a system, every watt conserved by turning off a heater, every piece of engineering gymnastics performed across 16 billion miles, it all comes back to keeping those two instruments running for as long as physically possible. Because the moment they go silent, that flow of information stops. There's no switching to another feed. There's no backup channel. The window simply closes. What comes next, in terms of another spacecraft reaching interstellar space, is a generational timescale. Any mission launched in the near future would need decades just to reach the heliopause. The scientists who designed the instruments on that hypothetical future mission would have to build on the foundation Voyager laid. They would inherit a set of revised models, a corrected understanding of the boundary region, a better map, all of it owed to the data trickling home from a spacecraft that was supposed to last 4 years. When Voyager finally goes quiet, that window into interstellar space will close, and we won't have another one for decades, if we're lucky. So what is the final message Voyager will ever send? It's not the last plasma wave reading. It's not the final magnetic field measurement or the last packet of engineering data that squeezes through the deep space network antennas before the signal drops below the threshold of detection. Those things matter enormously. They're irreplaceable, and the people at JPL are fighting for every last one of them. But they're not the message. The message is something that was decided in 1977, bolted to the side of a spacecraft, and launched into a future that nobody in that room would ever live to see. Here's the thing most people don't think about when they think about Voyager going silent. The silence is not the end. When the last transmission fades, probably sometime between 2030 and 2036, depending on how well the power management holds, the spacecraft doesn't stop. It doesn't slow down. There's nothing out there to slow it down. It just keeps going at roughly 38,000 miles per hour in the direction of the constellation Ophiuchus, carrying everything that was ever placed on board. The science ends. the conversation ends. But the mission, in the deepest sense of that word, continues indefinitely. So what does Voyager actually leave behind? Start with the science, because it deserves that much. For nearly 50 years, Voyager 1 has been sending back data from places no other instrument has ever reached. It crossed the heliopause in 2012 and entered interstellar space, a region that our models predicted but had never directly measured. What it found there was stranger than expected. The magnetic field was oriented differently. The plasma density was higher. The boundary between our solar system and the galaxy was not the clean transition that textbooks described. Every one of those surprises required us to revise something we thought we understood. That is not a small thing. That is what science is supposed to do. And Voyager has been doing it longer than most of the engineers currently working on the mission have been alive. When the signal finally stops, that window closes. No other spacecraft is close. New Horizons, launched in 2006, won't reach the heliopause for decades. The data Voyager is collecting right now, today, cannot be duplicated, cannot be approximated, cannot be replaced by a telescope or a simulation. It exists because one spacecraft went far enough and kept working long enough to get there. That's the scientific legacy. Irreplaceable, still accumulating, and almost gone. But then there's the other thing, the gold record, 12 inches across, gold-plated copper, sealed in an aluminum jacket with a stylus and a needle and instructions etched in symbolic language for anyone who might find it. 115 images. The sounds of earth, thunder, rain, wind, surf, a mother's first words to a newborn child. Greetings in 55 languages, spoken by people at Cornell who were given one instruction: say hello to the universe and keep it brief. 90 minutes of music. Bach, Beethoven, a pygmy girl's initiation song, Georgian choral music, Chuck Berry's Johnny B. Good, which someone on the selection committee objected to on the grounds that rock and roll was adolescent, and Carl Sagan replied that there were a lot of adolescents on the planet. The song stayed. Think about what went into that record. A committee of human beings sat down and tried to answer an impossible question. If you had 2 hours to explain humanity to a stranger who had never heard of us, what would you choose? They argued about it. They debated music selections and image choices and which languages to include. They compressed the acoustic life of an entire planet into a format that could theoretically be decoded by a civilization that had never met us. And then they sent it. It is now 16 billion miles away. No signal we could send would reach it in time to do anything. No spacecraft we could launch would catch it. It is gone, in the most complete sense of the word, except that it's still out there, still moving, still carrying everything they chose to put on it. When they selected those 115 images, they were choosing what to show about us: a man and woman in a wheat field, Andrew Wyeth's Christina's World, a sunset, a mother and child, a DNA molecule, a X-ray crystallography image of a DNA structure, because the committee understood that beauty and science were not separate things. They chose mathematical diagrams and geological formations and human faces from every continent. They chose to show that we could see, that we could think, that we could love, and that we could create things of beauty from the raw materials of our world. Those images represent thousands of conversations about what it means to be human, distilled into something that could fit on a disk and travel forever. That's where Ann Druyan's brainwaves come in. She sat in a laboratory at Bellevue Hospital in New York in 1977, wired up to a computer, and spent an hour thinking. She thought about the history of Earth. She thought about what it meant to be alive. She thought about falling in love. She and Carl Sagan had just become a couple, just days before the recording. The computer translated all of it into sound, her heartbeat, the electrical activity of her brain. 1 hour of thought, compressed into roughly a minute, encoded onto a gold disk and launched into interstellar space on a spacecraft that is now farther from Earth than any object humans have ever made. That is not a metaphor. Those are her actual thoughts, or as close to thoughts as we know how to record. They're out there right now, somewhere past the heliopause, past the edge of everything we've explored, riding a gold disk through interstellar space, in the dark, at 38,000 miles per hour. And here's what you have to sit with for a second. The data transmissions will stop. The magnetometer will go quiet. The plasma wave subsystem will send its last reading, and then there will be nothing. Engineers at JPL will send a command and wait 23 hours, and nothing will come back. And then Voyager 1 will become the most distant silent object in human history, a machine still moving, still carrying everything, just no longer able to say so. But the record doesn't need power. The record doesn't need a transmitter, or a functioning RTG, or a thermocouple that hasn't degraded. It doesn't need anything. It's a physical object, protected by a metal jacket, attached to a spacecraft moving through a near-perfect vacuum where almost nothing can damage it. In 40,000 years, Voyager 1 will pass within 1.7 light-years of the star Gliese 445. The record will still be there. In several billion years, when the sun expands and the inner solar system is consumed, the record will still be there. There is no realistic mechanism by which it gets destroyed. It will simply keep going. So the final message Voyager sends is not a transmission. The final message is the record itself, the physical object moving through space at 38,000 miles per hour, containing everything a group of humans in 1977 thought was worth saving. Not a summary of our science, not a political statement, something closer to a portrait. The sound of thunder, the sound of a newborn, the music humans made when they were happy and when they were searching for something they couldn't name. The thoughts of a woman in love, encoded in the electrical patterns of her brain. Greetings in 55 languages from people who had no idea what they were really saying goodbye to. It's not "we were here." That's too simple. It's closer to "this is what it was like." This is what we sounded like when we tried to tell each other the truth. This is what we thought beauty was. This is what happened in our brains when we fell in love. This is a mother talking to her child for the first time. This is Chuck Berry, because yes, we had adolescents, and they made music, and we thought you should know that. The spacecraft was built to last 4 years. It lasted nearly 50. It was sent to study Jupiter and Saturn, and it ended up in interstellar space. Every single thing about Voyager's existence has exceeded what anyone asked of it. And when the last watt is spent, when the engineers at JPL listen for a signal that doesn't come, the spacecraft will still have one thing left to do, the only thing it was ever going to do forever. Keep going, and it will keep going, carrying all of it, the music, the heartbeat, the brainwaves of a woman in love, the greetings in 55 languages, the sounds of rain and thunder, and a mother's first words to her child. Out into a darkness so vast that even light takes years to cross it, moving away from us forever, never stopping, the most human thing we ever threw into the cosmos.